Let me go back to my questions. Who can give me an example of something we've seen that's a subspace? If H is a quadrant, is this a subspace? You give me something, I draw it. Is this a subspace? Take a vector here, you scale it. Do you say within your subspace? No. Subspace have satisfy all the properties. Okay, anybody else? X plus 2y equal to 0. Now what's characterize x plus 2y equal to 0? So x plus 2y equal to 0, basically what? That's because if I take two vectors, regardless how you take them and add them, you never leave your subspace. And if you reflect them, you never leave them as well. Okay, now, can you give me another one? So that's a line, basically. Is this the only one? Try to generalize. What's going to be the generalization of that? Any line through the origin. Any line through the origin is a subspace. Important. Any line through the origin is a subspace. Now, what other subspaces are? Now, watch carefully. Every time we have a subspace, every time H, that's how it works. Every time H has two vectors, so suppose H is not a line. So if H is a line, I'm done. So suppose H is not a line. Every time you have two vectors in H, you will have every linear combination of those two vectors. That's a subspace. So if you have two vectors, you have every linear combination. Means regardless how you move in the direction of, if you move a little bit in the direction so of one in direction of the other, and you add those somehow, your new vector has to be in H. So once one vector is in H, two vectors are in H, every linear combination of them is in it. It means all of R2 will be in H. So another example of subspaces, R2 itself is a subspace. Now, of course, this is a subspace because adding two vectors in R2, you're not going to add in R3. Scaling a vector in R2, you don't add in, not going to add in R3, and 0 is in R2. So that's a subspace. So now lines and R2. Who can think of another one? That on this object in R2, they have specific property. Okay, anybody can think of another one? Another subspace. The subspace that consists of, so suppose H consists of the 0 vector only. Only. That's a subspace because 0 is in it. Adding two zeros, you still have a 0. Scaling is 0, you have a 0. And these are basically the only subspaces of R2. There is nothing else in R2, which is, we call a subspace. So there are those lines through the origin, basically, that's important. And those will be called subspaces of dimension 1. They are R2 and the 0 itself, okay? Now, using the same kind of logic, we can generalize to the subspaces of R3. It means collection of vector in R3. And the subspace of R3 would be R3 itself. So H equal R3. H equal 0. Means consists of the 0 vector. And what else? If I'm in R3, if you take any line through the origin, any line through the origin, that's a subspace because you take any line for the same reason. adding a line, adding two vectors on the line, so every line through the origin. And all right. And what else do you think? You can give me one more example, just by generalization. So you are in R3. If you take a line in R3, so that's a subspace because all the conditions are satisfied. We can think of one more subspace in R3, one more collection of vectors that have this property. A plane, absolutely a plane in R3. You take any plane in R3, as long as it goes through the origin, then take any vector in it, add them. You never leave your plane because you are within the plane, adding them. And if you have a vector in R3 and scale it, you never leave the plane. So every plane in R3. So this will give us a little bit, some kind of a picture, every plane through the origin. This helps us a little bit. When I say a subspace of R3, you can start thinking, okay, that's a line, that's a plane through R3, or it is all of R3. Okay? So this is as abstract as I will cover subspaces of R, or the idea of a subspaces. You will have homework for next time to deal with that. For the last few minutes, we will do the following. Now we're gonna associate to, so now we're gonna go back to matrices, and to every matrix, we are gonna associate subspaces, okay? And that's the one that I will associate to a matrix. So something called, it's still 2.8, nothing. And it's the null space. Very easy, nothing hard. Okay, null space. So example of a subspace associated to a matrix, the null space. That's my definition. What's the null space? Suppose I have a matrix, matrix A. A matrix, nothing more, nothing less. And we solve the system, Ax equal to 0. And we have a lot of solution. The collection of all the solution is called the null of A. So let me read it again. Let A be an n by n matrix. The null space of A, denoted by null of A, is the set of all solutions of the homogeneous system Ax equal to 0. Okay, so that's the solution of all the homogeneous system. Now we are in a more familiar territory. Now, so the null of A is all the x's. And let's see why it's Rn here. All the x's, such that A times x equal to 0. And why did I say Rn? Because suppose A m by n, so this is A, and that's m by n. The null are, so it's m, what did I say here? M by n. The null are all those vectors, those x's. They are the solution. That when you take A, you multiply by them, you get the 0 vector. So that's really what the null of A is. Okay. So, and it's in Rn because the matrix is n by n. So this vector here has to be in Rn. Now let's take a simple example. So I gave you a matrix A. And that's the matrix. And that's a vector. And my question is x in the null. Now, to answer this question, you have to go back and say, okay, well, what is the null? The null is nothing more than all the solution of the system Ax equal to 0. Okay, that's really what the null, everything that's solved. So if I ask you, is x is the null, I'm really asking you, is x is the solution of Ax equal to 0? Because my question is, x is the null, it means basically we need to check if A times x equal to 0. So it is really the solution of the system. Okay, so it's something we're very familiar with by the stage. So I check it out. Okay, we can check it. We take A times x. That's my A, that's my X, and I multiply them, and I will get 0, 0. It means my X is in the null. Okay, so that's really what the null space is, all the solution. Now, the null is a subspace. That's really the hard part. What does it mean? The null is a subspace. It means that, I'm going to talk about it in a second. It means that if you take two vectors, which are solution of the system, you add them, you get another solution of the system. That's really what it means, a subspace for us here. You take a vector which solves the system, like this one, and you scale it, you get a new solution of the system. So that's really what the idea of a subspace, and that's really how it's used mathematically. So when we show that something is a subspace, it means we are telling you that once you have two things in it, their sum and their scalar multiplication will also satisfy the same property. So let us see why is that. I can have it. So let's see what it is. I know it's a lot of math for you, but okay. So if A is an n by n matrix, then the null is a subspace of Rn. Okay, so it means, all right, so what does this mean? Let's see why. First, 0 is in the null. Why it is in the null? The null are all the solution of Ax equal to 0. 0 is in the null because if I take A, whatever A is, I multiply by the 0 vector, I get the 0 vector. It means 0 is in the null. Okay? Now, this tells me that if you have two vectors which are solution of the system, their sum, this is another vector, is also a solution. Well, that's not really hard. That's really the heart of what subspace is really about. So let's see why. So suppose, suppose I have two vectors in the null. And we have to show that the sum is also in the null. And let us see why. So if X solves the system, X equals 0. And Y solves the system. It means AY equal to 0. And when I look at A times this new vector, X plus Y, will this be a solution? Is X plus Y a new solution of the system? That's really what this is about. Now, the product of matrix by vector tells me that you can distribute A. So this is going to give me A times X plus A times Y. Now, if X is a solution, this is 0, which gives you 0. So if I give you any two solutions of the system, immediately you should know that their sum also is a solution, the homogeneous system, and that's really crucial. Again, if I take a vector, let's see, be a scalar, X in the null, to show that Cx in the null. All right, if I take a vector scalar, so let me start a vector in the null. It means X is a solution, and I scale it. Well, I get another solution. Okay, I take A times Cx. All right, now the property of matrix, then you can take this C out. So that's C times X. A times X is 0 because X in the null. So that's going to give me C times 0, which is equal to the 0 vector. Okay, so this is telling us what's really the heart of subspaces, that if somebody tell you, this collection is a subspace, which is usually people try not to use it a lot because students don't know it. They mean that whenever they give you two things in it, adding them, scaling them will also have to satisfy this property. So we finish with a something simple example. So actually here I'm trying to explain it a little bit more. So this tells us that if X and Y are in the null, that is if X and Y are solution, then every linear combination of X and Y is also a solution. That's really what I'm saying. So suppose I give you A, that's the matrix. And I tell you U and V are in the null. All right, so I'm already telling you that A times U equals 0. That's what I'm telling you. And A times V equal to 0. That's really what I'm telling you. And here I'm asking you, give me 5 other vectors in the null. So I'm giving you 2 vectors, and I want you to give me 4 other vectors in the null. Okay? Is it a hard or an easy question based on what I've been talking about? Okay, and that's the last question, and then we quit. Go ahead. So those 2 vectors are in the null. If I take A times U and I multiply it, I get 1, minus 1, bunch of 0, 2, minus 2, bunch of 0, 3, minus 3, 0. So I've got all zeros. Now my question to you, I want other vectors in the null. So I give you 2 solutions, gives me others. Being a subspace, it tells me what? If U and V in the null, what will happen? Take any collection of them. That's a vector in the null. Take 5U minus 6V. This is a new solution of the system. That's really what it means. And we can keep going forever. 100U, every linear combination of them, minus 7V is also a solution. So if I have 2 solutions, I can actually, you can give me infinitely many solutions of the homogeneous system. And homogeneous is really important. Okay, so I stop here. Before we go, I think if my memory is correct, because things are not working the way I want them to. You guys had an exam this coming Monday, Wednesday, correct? Yes or no? Okay, so definitely you're not going to have. I never do that. What about having it on Monday? Will it be okay? I will send a message to all of you. Is it okay to have the test on Monday? All right, great. So I will tonight, when I take a break and relax a little bit, I will put up review for you guys, and you look at it, you do the homework. It's going to be a little bit later, not now. And you have questions on Wednesday. It will be your last chance to ask me questions. All right? Can you pull up the theorem paper? Okay, I think. Is it this one you're looking for? Okay, go ahead. All right, are you guys done? All right, I'll see you on Monday. Bye-bye, guys. No, okay, I'll keep it. Thank you. Bye-bye, guys.